So our class was based on rock-forming minerals today, and really we differentiated between silicates and non-silicates. And I don't want to make it seem like we got to overthink this. If it's a silicate, it contains both silicon and oxygen. And if it's a non-silicate, it doesn't have both. So it cannot have both silicon and oxygen. It can have silicon or it can have oxygen, but it cannot have them both. So the Earth's crust is dominated by about 94% silicate minerals. So that makes silicate chemistry significant. That's simply saying that the majority of minerals within the Earth's crust, right? We're studying the surface of the Earth, and that's in the form of its crust. It's just dominated by silicon and oxygen. So if I look down here in my percentage by weight, you'll find that oxygen is about 47% of the Earth's crust, and silicon is about 28%. That's a tremendous amount. That's roughly 74% of the total Earth's crust by weight is silicon and oxygen. So it should be pretty common to you, it should make sense to you, that silicon and oxygen are going to be prevalent in most rock-forming minerals. So here's some new material we added today. Light-colored minerals contain silicon, oxygen, aluminum, calcium, sodium, and potassium. These light-colored minerals are called felsic minerals, and they lack iron and magnesium. They're light in color, and they are silicates, so we call them felsic minerals. Dark-colored silicate minerals contain iron and, it should be and or magnesium. Dark silicate minerals are called mafic minerals. So if I look at my list of what primary elements are found within the Earth's crust, you'll find that I have oxygen, silicon, aluminum, and then iron. Iron is only 5% of the Earth's crust by weight, but that's enough for it to just kind of find its way into some silicate minerals to make them mafic. And if they're mafic, they're dark. So calcium comes in next, 3.6 or roughly 4%, then sodium at about 3%, potassium, slightly less than sodium, and magnesium, about 2%. So we have these 8 primary minerals that are going to dominate the Earth's crust. And we've defined them that these are all silicates. Felsic and mafic are both silicates, but felsic are light in color and mafic are dark in color. And as soon as we add iron and or magnesium, the mineral gets dark really quickly. So here's just a pie chart that's depicting these same percentages over here. Clearly oxygen dominates and then silicon. But here's the names of the minerals that dominate the Earth's crust. So here I have plagioclase, which is roughly 39%. This is a feldspar. And orthoclase, which is also a feldspar. And between plagioclase and orthoclase, you've got over 51% of all the minerals found in the Earth's crust are feldspars. So feldspars are silicates, and they are felsic silicates, felsic minerals, so they are light in color. So notice plagioclase in our mineral set in class is white, and orthoclase is kind of a salmony color or pink color. Here I have quartz, which is silicon dioxide or SiO2, and then I've got pyroxene, which is 11%, and I start breaking down into smaller groups where I have my micas, my amphibole, I have olivine, which is all the way down at 3%, and then others, these are typically non-silicates, at about 8.4%. So the Earth is dominated by silicate chemistry. So since we're talking about silicates, we have to talk about the silicon-oxygen tetrahedron. And it's simply saying that I have one silicon atom surrounded by 4 oxygen atoms. And these are what bind or bond silicate chemistry together. So this primary tetrahedron, or this is a shape that is very common to silicate chemistry. Silica is the basic building block of all silicate minerals. These consist internally of a central silicon atom that shares a pair of electrons with each of 4 neighboring oxygen atoms, forming strong covalent bonds. So really what I'm talking about here, silicon and oxygen, I create this shape, this tetrahedron, if you will, this 4-sided three-dimensional object that has, let's just say strong covalent bonds. So the diagram in here is depicting all atoms in a single plane. Is a 2-dimensional representation of what is actually a 3-dimensional structure, the silicate tetrahedron. So here's what we got into today. We just began to dabble, but let's make some sense of this. Single tetrahedrons are just those tetrahedron shape that we pointed out here on this page, or that I pointed out. They're all based on this. These are single tetrahedrons. But when I start getting more sophisticated with the chemistry, I start putting these tetrahedrons together and I get what are called single chains. If I start putting these single chains together, right? If I take pyroxene or augite and I start putting these single chains together, I get double chains. And these are, once again, just tetrahedron that are linked by these bonds into now double chains, and I get amphibole or hornblende. All right, all three of these are mafic minerals. But you'll notice something's about to happen. I've got these mafic minerals that have iron and or magnesium, and then you'll find that I've got biotite mica, and these come in sheets. So if I start putting these double chains together, I start getting these sheeted characteristics. And here's my biotite mica. But you'll notice I've got olivine, pyroxene, and amphibole, and then into biotite mica. These are all mafic minerals. From here, I now move into muscovite mica, which is still a silicate, but it's now a felsic mineral, into my three-dimensional networks. And these are the most complex, the most sophisticated. These are where the single tetrahedra are now all over the place in the three-dimensional network. Very, very strong covalent bonds. These are also some of the harder minerals because of those strong covalent bonds. So my feldspars, both orthoclase, which is in the picture here, and plagioclase, and quartz both have hardnesses between 6 to 7. So those are fairly hard on most hardness scale. So when I compare mafic minerals, I'm going to compare augite or pyroxene, these are just synonymous, to hornblende, which is amphibole. You'll notice that augite, and this is something you need to make sure you understand how these work, because the cleavage planes are very, very important to differentiate between pyroxene and amphibole. So let me give you a little bit of a heads up. When you find the cleavage planes of these two minerals, for example, augite or pyroxene is going to have a 90-degree intersection of the cleavage planes, where amphibole or hornblende is going to have a 60-degree angle and a 120-degree angle. Right? These interior angles must equal 180. So I think you need to make sure you're paying attention to, well, if the angle is 90 degrees, it must be pyroxene or augite. If it's not at 90 degrees, it's hornblende or amphibole. Not going to lie, I'm going to give you a little secret of mine. I've always said greater than 90 degrees, this 120. I always thought, like, I don't know, I always used to think of, this is going to sound silly, but H-A-M, ham, eating pork, I don't know, beefier, porkier. 120 degrees is a lot more than 90. I don't know. You find your own way of figuring that out, but it works for me. Good luck to you. And lastly, non-silicates. We've got oxide groups. These have O2 subgroups. Sulfides are just sulfur compound. Sulfates are SO4 groups. Halides, chlorine, fluoride, or bromine. I have carbonates, which are a CO3 group, and native elements. These are just elements in their native state. So these are examples that you can take a look at. But notice that non-silicates make up about 8% of the Earth's crust. Some are major constituents of sedimentary rocks: calcite, dolomite, gypsum, and halite. But remember, this is non-silicate chemistry. This last slide are the non-silicates. Most of the Earth's crust, or by 92-94%, are silicate chemistry. These are the 6 groups of non-silicates. So there you have it.